Okay, hope everybody had a good day. What we're going to do today is we are going to study a new law in the study of electrical engineering technology. It's a little bit more abstract, but it's a whole lot easier than Ohm's law. Remember Ohm's law is that big wheel of formulas, right? It's in the very back of your book, okay? What I'd like you to do is I'd like you to turn back to the index of your book, to the very back, okay? And I'd like you to look under the letter K. Look under the letter K, because I just want you to get used to where to find this, okay? And I want you to help me with a little spelling exercise here, okay? How do you spell Kirchhoff's? K-I-R-C-H K-I-R-C-H-O-F-F. Kirchhoff's voltage law. There's two of them. There's Kirchhoff's current law and Kirchhoff's voltage law. Tonight we're going to be talking about Kirchhoff's voltage law. Okay? Now, Kirchhoff's voltage law is something that can be presented in a way that's hard to understand or easy to understand. I'm going to tell you both ways, but obviously we're going to use the easy way, because there's no point in making anything harder than it needs to be. Okay, what I want you to understand is that any time that I write something in the process of solving a problem, and let's say I'm using Ohm's law, okay, then I might write something like this. By Ohm's law, okay, voltage equals current times resistance. That's one of Ohm's law's formulas, isn't it? Okay? So that would be an example of Ohm's law. Okay? Now, when I'm using Kirchhoff's voltage law, I will never, for the rest of this semester, write this out. Number one, I can't remember how to spell it. It just takes too long. It takes too long to write it out, and it takes up too much space. So what I'll write is, I will write by Kirchhoff's voltage law. Okay? So whenever you see that right there, by Kirchhoff's voltage law, that's what I'm basically referring to, is a law in electrical engineering referred to as Kirchhoff's voltage law. Okay? And we're going to talk about what it is in just a second, but I just want you to understand the nomenclature, the spelling, the abbreviation, etc. Okay? Let me give you an example of Kirchhoff's voltage law. Kirchhoff's voltage law, stated in a sentence, says that the sum of the voltage drops, I'm going to write this down, the sum of the voltage drops around any, and I'm emphasizing any, around any closed loop equals 0. The sum of the voltage drops around any closed loop equals 0. That's the formal way of stating Kirchhoff's voltage law. Okay? Now I'm going to show you the way that we're going to simplify this so that we can use it to solve circuits and to predict how big wires have to be and how big breakers have to be and what size panels have to be and things that make you money. Okay? Kirchhoff's voltage law, if we're given a circuit, and let's say in the circuit we just have a battery that's 12 volts, just like your car. So the source voltage is 12 volts. Okay? And we have one resistor over here. This might be the filament in a toaster. And this is the resistor of the load. And this is equal to, let's say, 100 ohms. Okay? Kirchhoff's voltage law, in one form, says the sum of the voltage drops around any closed loop equals 0. Now, first of all, would it be fair for me to say that this is a closed loop? Would that be a fair statement? Yeah, that's a fair statement. That is a closed loop. Okay? The easier way to remember Kirchhoff's voltage law is that the source voltage must be equal to the sum of the voltage drops around the loop. Well, there's only one place that there's a voltage drop if you ignore the wires. Right? So if this voltage must be equal to this voltage, then how many volts is across that resistor? 12 volts. Okay? Now, let me modify this a little bit and stick two resistors in here. But let's make them equal resistors. This is 100 ohms, resistor 1. Resistor 2 is also 100 ohms. Okay? Remember, the simple form of Kirchhoff's voltage law says the source voltage must be equal to the sum of the voltage drops around any closed loop. Now, first question, would it be a fair statement to say this is a closed loop? Okay, so does Kirchhoff's voltage law have to apply to this loop? Yes. The answer is yes, it does. Okay? So Kirchhoff's voltage law says that this source voltage must be equal to this drop plus this drop. Now, since these are equal resistors, would it be fair to say they have equal voltage drops? Okay? Since this is 12, would it be fair to say that this would be half and this would be half? Okay? So just by using Kirchhoff's voltage law and looking at the values of these resistors, we can say that if this is 12 volts and Kirchhoff's voltage law says the source voltage must be equal to this drop plus this drop, okay, then we can say that resistor 1 has a voltage drop of 6 volts, resistor 2 has a voltage drop of 6 volts. Now, let's say we wanted to check our theory here. Okay? Well, one way we could do it is we could find an equivalent circuit. Okay? Do you remember when we studied about series resistors? In other words, resistors that are stacked like money, right? You know, if I got 100 and I put another 100 on it, I got 200 and 300 and 400. They add algebraically. Okay? So if I wanted to, let's say, make an equivalent circuit down here, a little bit lower, I had the same 12 volt supply, but I wanted to represent the load with one single resistor. okay, then our total would have to be equal to R1 plus what? R2. R2. So that would be equal to 100 plus 100, obviously in ohms. And 100 plus 100 is 200, right? So the value of this total resistance would be 200 ohms. Are you with me? Now, if I tell you that this is 12 volts and this is 200 ohms, would it be fair to say that this is a closed loop? Okay? If this is a closed loop and there's only one source and one load, and the source has 12 volts, what does the load got to have on it? 12 volts. 12 volts. Okay? So if this has 12 volts on it, then how much current is flowing through the resistor? Well, let's use Ohm's law, right? Okay? We want to know what current is flowing through the load. And what is it that we have? We have voltage and we have resistance. So what is a formula from Ohm's law that will give us current or amps if we have E and R? E divided by R. E divided by R, which is equal to 120 divided by 200. So what is that equal to? 0.060. Is that right? Okay, so we'll just write it as 0.06. Okay, now, if the current that's flowing here, and since we've already figured out that this is 0.06 amps, then I'm just going to erase this so it's less cluttered. If we've figured out that the current flowing here is 0.06, then what is the current flowing here? 0.06. And since this is a series circuit, what's the current that's flowing in every single resistor? 0.06. So if I wanted to use the current to figure out what the voltage drop was across this resistor, okay, then I would go to Ohm's law and I would find a formula that says voltage is equal to what? Current times resistance, because that's the Ohm's law formula for it, right? So voltage is equal to current multiplied by resistance. So the current is 0.06 and the resistance is 100. What's 0.06 times 100? 6. So that means there's 6 volts dropped here and 6 volts dropped here. Well, didn't we just figure that out with Kirchhoff's voltage law? Two ways to do the same thing. You can use Kirchhoff's voltage law to figure out this problem, or you can simplify the circuit, use Ohm's law to figure out the current, and then come back and use Ohm's law again to figure out the voltage. Okay? So what we want is we want to have like 2 or 3 or 4 simple tools at our hands. Okay? And then when we have those simple tools at our hands, we're able to figure out a whole multitude of things, and there's a whole lot of different ways that we can do it. Now, if we move over to this board right here and create a completely different problem, call this example number 2. And let's just say that in this problem, we had a DC voltage, and somebody give me a number. Okay, we'll go with 60. So the source voltage is equal to 60 volts. Okay? And let's say that we had two resistors. Two resistors. This is resistor 1. This is resistor 2. Okay? Now, somebody give me a value for resistor 1. And the reason I'm saying give me a value is because I want to show you that it doesn't matter what value it is, the theories always work. Okay? Somebody give me a number. 30 ohms. 30 ohms. Somebody give me a number for that one. 5,000 ohms. 5,000 ohms. Okay. Now, in this circuit right here, what I want to do is a couple of things. I want to figure out, number one, how much current is that load drawing? Okay? And the way that we've learned previously to figure out how much current that load is drawing is to simplify the circuit so that instead of having two resistors, we only have one. Right? How are those resistors connected? They're in series. Okay? So the total resistance, if they're in series, is equal to resistor 1 plus resistor 2, which would be equal to 30 plus 5,000, right? Which would be equal to 5,030 ohms. Okay? We can then move over and draw an equivalent circuit where we have the same source, which is 60 volts, but we have only one resistor. And that one resistor has a resistance of 5030 ohms. Are those equivalent circuits? Is this circuit equivalent to that circuit electrically? Yeah. Okay. When we only have one battery and one resistor, is it pretty easy to use Ohm's law to figure out the current? Yeah. If we want to figure out the current that's flowing here, okay, then we can use Ohm's law. So if I wanted to, I could write by Ohm's law. I usually don't do that, but we could write by Ohm's law, current is equal to, now I have to go to my Ohm's law wheel and find out what current is equal to in terms of E and R. Because remember, this is the total voltage and this is the total resistance. So what's the formula? E divided by R. So current is the ratio of voltage divided by opposition to current flow. So that's going to be equal to 60 divided by 5030, or 5030 ohms. So when we calculate that, what do we get?
0.12.
I'm sorry, what is it? 0.01. 0.012. So 0.012 amps. You got something different?
0.0119284.
Okay. Everybody who has a calculator,
I got that.
you got this number here?
No, I got the number 0.11924.
Oh, okay. Okay, well let's go ahead and take it out to one more digit. So if we do that, then it's 0.01 0.019, right?
Yeah.
9. Okay? Okay? Or 11.9 milliamps. You see how that decimal, if you move it over 1, 2, 3 places, it'll be 11.9 milliamps. Okay? All right. If the current is 11.9 milliamps, or 0.0119 amps, in the equivalent circuit, what would the current be in this circuit that we started out with? It would be the same. Right. So this would be 0.0119 amps flowing in that circuit right there. Now, using Ohm's law, what would the voltage drop across resistor 1 be? Well, using Ohm's law, if we know the amps, or the I, the current, and the R, or the resistance, what would the formula be? Voltage is equal to current times resistance, right? So it would be current times resistance. So for resistor 1, because remember the currents are the same through both resistors, I'm just doing the top one first. The voltage drop on resistor 1 would be equal to 0.0119 amps multiplied by the resistance, which is 30 ohms. So what do we get for that? 3.57 volts. Is everybody in agreement with that? No?
I got 0.357.
I got 0.357.
0.3, try it again, Hans. 0.0119 times 30.
I got 0.357.
Okay, so we're getting two answers, and I don't have a calculator in front of me. Okay, so are you putting in 0.0119 times 30, and what are you getting?
That's the same, 0.357.
Okay, so you're getting 0.357.
I concur.
Okay, so everybody concurs. Let's just make sure that we make sure Hans's calculator's not gone off the blade. 0.357. Okay. So it's 0.357. Important to keep track of those details. Okay? Good. Good job. Good deal. Okay.
That's the biggest problem with this, is trusting your answer on the computer.
Well, yeah, and that's a nice thing about the nicer computers or calculators, is that you can look at the numbers you punched in and you can see if they were the right number.
I got something different on the other answer. On your first problem, you had a 0.06 and I had like just 0.6.
Huh. Okay. All right. Well, we're all in agreement here, right? This is 0.357 volts. Okay. So let's calculate the voltage drop on resistor number 2. That's going to be equal to what? The current flowing in resistor 2, which is 0.0119, right? Times resistor number 2, which is 5,000. So that's going to be 0.0119 amps times 5,000 ohms. 59, you getting that, Haas? 59.5. Okay. 59.5 volts. Okay? Now, we are going to use the voltage drops that we just calculated, okay, to test Kirchhoff's voltage law. The voltage drop that we just calculated across this resistor right here, I could represent by bringing a couple of lines out from here and writing down what the voltage drop on resistor 1 was. That's 0.357. 0.357. I could write down the voltage drop here by just bringing a line out and writing an arrow between here and here. That would be 59.5. So this is 59.5. And of course, those are volts. Now, Kirchhoff's voltage law says, well, hold on a second. First question you have to ask when you're dealing with Kirchhoff's voltage law, would it be fair for me to say that this is a closed loop? Would Kirchhoff's voltage law have to apply to it if it's a closed loop? Does Kirchhoff's voltage law say that the voltage here has to be this plus this?
Yes.
Okay. What is this plus this in volts? 59.5 plus 0.357. So when we round it up, because obviously we had some error that was induced in this, okay, it rounds up to what? 60, right? Because when you add it up, what do you get? You get 59 point what? 0.857 volts. If you were going to round that up to the nearest volt, what would it round up to? 60. Now, why aren't we getting exactly 60? Well, the reason we're not getting exactly 60 is because we didn't take this out to as many decimals as it could go, or this, or this, or the current. Yeah. If we would have done that, then we'd get exactly 60. Okay? Now, there is
We wrote that out in the, like you have the voltage total of 60 volts up there, the voltage drop would be EV.
I'm sorry, I didn't totally understand. What's that?
Just the,
He's talking about the notation of the voltage drop across a resistor, like ER. Like
Yeah,
the
there's
voltage of the resistor.
yeah, there's a lot of different ways that you can decide you're going to use notation. It's like nicknames. You know, it's like Frankie, Johnny, Mikey, you know, whatever. And that can all be the same person, right? This resistor right here, you know, can be the resistor of the L, which could be the same thing as the resistor of the load, which could be the same thing as the resistor of the toaster. You know, it just depends on what you're talking about. Those could all be the same thing. I mean, we might want to say, rather than writing out the word toaster, let's just put L because the toaster is our load. Okay? Does that answer your question? Yeah. All right. Now, what I'd like you to do is, again, look in your books, and I would like you to look up the voltage divider formula. There's a formula that we're going to learn where we can figure out the voltage drop across the resistor by just using the ratios of the resistors and the source voltage. So see if you can find that. Look in your index of your book, look up voltage divider formula, and then turn to the page where it has the formula and tell me what the formula is. I know the formula, but I want you to do that so that if you forget it, you know how to go find it. Hans.
I got it. It's EX or E source equals RX divided by R total multiplied by E total. Actually, the parentheses go around the RX and R total.
Okay. Okay. It doesn't matter really which way you do it, but we'll do it the book's way. Thank you for that clarification. Okay, if you haven't found it, just go ahead and write it in your notes, and then you can. Did you turn to the page in your book, or did you just have that in your cheater sheet?
I had the notes ready.
Oh, page 158. Page 158. So if you still haven't found it, it's on page 158. Okay? All right, now, this is a kind of useful formula if you're just looking for the voltage drop across one resistor and that's all you care about. Let me show you an example. Let's say that we're given the following circuit. We're given a voltage source, so this would be ET. In our book likes to call voltage by the letter E, okay, and it likes to call the voltage source by the letter E sub T. This is called a subscript. When you write the letter down lower, it's called a subscript, okay? So you notice here how I wrote total, okay? That's the same thing as ET, okay? All right, now let's say that we had a source voltage and somebody give me just an odd number, not an even number. 62 volts. Okay? And then let's say that we had two resistors that were in series. Now, this circuit right here, this is R1, this is R2, let's say. Okay? This circuit right here, before we go any further and we assign values to the resistors, which you're going to choose, okay? This circuit is called a voltage divider. Why is it called a voltage divider? The reason it's called a voltage divider is because this whole 62 volts, which let's say is all the money I have in the bank, okay? I got to give some of it to this resistor in the form of a voltage drop, and I got to give some of it to this resistor, right? If I had $62 and I gave it all to you, there wouldn't be any money to give to you. right? So that would mean there could only be one resistor in the circuit. If there's two resistors in the circuit, then the voltage is going to divide up. Understand? Okay? So somebody give me a value for resistor number 1.
31.
31 ohms. And somebody give me value for resistor 2 that's less than 700.
699.
Okay. 699 ohms. Now, this is the way that this formula works, and it's pretty cool. Remember before, if we wanted to know what the voltage drop was here, then we'd have to reduce the circuit down to one resistor by using the series formula for finding the total equivalent resistance. And then we would have to figure out the current, and then we'd have to go back and figure out, that the current was the same in this circuit as the equivalent circuit, and then use Ohm's law to figure out the voltage drop on that resistor. Okay? This formula does all that for us in one shot. Let me show you how it does it. E sub x, remember in algebra, do you remember in high school what x usually stood for? An unknown. Something that you were looking for. X was the thing you were looking for. Okay? So in this formula right here, this is going to represent the voltage drop across the resistor that we're interested in. So which resistor are we interested in? You tell me. R1? Okay. So this guy right here, we're going to make this guy Rx. That's the one that we're interested in. Okay? It's still R1. I mean, R1 is still equal to Rx, but it's the one that we're interested in. Okay? Now, this right here, E sub t, is equal to what?
62.
The source voltage. 62 volts. Okay? R sub x would be equal to what? 31 ohms. Okay? What about R total? This is where the rocket science comes in. Yeah, it would be the series combination of the two resistors. It would be like counting money, right? It would be like counting money. It would be the series sum of the two resistors, okay? So R total would be R1 plus R2. So if we were to rewrite this, we could rewrite this as the voltage drop across resistor number 1. Well, actually, let's even be more specific. The voltage drop across the 31 ohm resistor is equal to the resistance of the 31 ohm resistor. That's 31 ohms. Divided by the total resistance. Well, that would be 699 plus 31. What is that? 730. So I'm going to erase that and write down the sum of 31 and 699. So that would be 730 ohms. And then this is multiplied by what? 62, which is the source voltage. And what is the unit on the 62? Volts. And what happens to the unit of ohms? They cancel out. Because remember, anything over itself is 1. Okay? So now, get your calculators out and go 31 divided by 730 times 62 equals?
2.632.
So the voltage drop right here across this resistor is what? 2.632?
Yeah. 40 divided by 3.
Okay. All right. So do you see how we didn't have to do any of that, combining of the resistors and finding the equivalent circuit and all that? And we could just find the voltage drop across that resistor. Boom, just like that. Okay, now let's redo it for R2. So I'm going to erase this. Okay? And we're going to use the same formula, but this time we're going to find the voltage drop across resistor 2. So this time R sub x is going to be resistor 2. In other words, that's the one that we're interested in. Okay? So if that's the one that we're interested in, then our formula would look like this. The voltage drop across resistor 2, or the 699 ohm resistor, would be equal to the value of that resistor, which is 699 ohms, divided by the total resistance. The total resistance is 699 plus 31. And what did we find that to be? 730. That didn't change. This is 730. And then that is multiplied by what? 62. That's multiplied by 62 volts. Our ohms cancel. We're left with volts. So get your calculators out and tell me what 699 divided by 730 times 62 is.
59.36.
This is equal to 59.36. Now, is it fair to say that this is a closed loop?
Yes.
Does Kirchhoff's voltage law have to apply to a closed loop? Yes. Okay. So is it true then that this voltage must be equal to this drop plus this drop?
Yes.
Okay. What's this drop plus this drop?
62.
Pretty darn close to 62 if we, take into account our rounding errors. So thus we have verified Kirchhoff's voltage law like 3 different ways. Okay? So for homework tonight, look up that formula and do some practice problems with it. Okay? Because it's going to be extremely valuable when we start getting into more complex circuits. All right? Have a good night.